Share the screen. That, that. All right, we're ready to roll. So today we're going to go to module 4, but before we do, I want to introduce a concept. We have angular speed versus linear speed. All right, so angular speed is an angle per time, whereas linear speed is a distance per time. So linear speed is like what your speedometer in your car tells you, something like miles per hour, right? Angular speed is like an angle per time, right? So another example would be like, what about like laps, right? They use angular speed when we're talking about like revolutions, like one lap. That's the same thing as one revolution. So you can imagine like helicopter blades, anything that spins, you might prefer to talk about angle per time instead of distance per time. Okay, makes sense. So how would we like switch between the two? Well, let's do an example. Let's say this driver is driving. He's going 3 laps per hour. So what is the angular speed? Right. Well, if one lap, right, is 2 pi radians or 360 degrees, right? We would just say the angular speed would be angle per time or 3 laps. If a lap is 2 pi, this would be 6 pi per hour. That would be the angular speed, right? It's an angle per time. Now, well, how fast is he going? What would a speedometer say, right? Well, it depends on how big a lap is, right? So we need some more information. So what if they didn't tell you how far a lap was? What if instead they just gave you the radius? Huh? What if let's say the radius is, I don't know, pi over 4 units of length, miles. We'll do pi over 4 miles, okay? When you do problems like this, always write the units, all right? They guide you. So the linear speed, which would be a distance per time, right? We need to know, well, what is the distance of a lap, right? So we could write a lap in terms of angle, but we need to know the circumference of the circle. So circumference is 2 pi r. So the circumference is 1 lap as far as length instead of angle, right? So we would have 2 pi. If the radius is pi over 4 miles, let's not do pi over 4. That looks stupid. Let's just do a quarter mile. All right. So the radius is a quarter mile. All right. So the circumference would be pi over 2 miles. So that's the length of 1 lap circumference, right? And what is this? This is pi is approximately 3, right? So this is around a mile and a half, right? So now that we know what the length of 1 lap is, what is our linear speed here? A linear speed, well, the distance he's traveling is 3 laps per hour, right? So we'd replace lap with pi over 2 miles, and this is per hour, okay? So we're getting 3 pi over 2 miles per hour. Well, if pi is approximately 3, 3 times 3 is approximately 9. So this is approximately 9 halves, which is what? 4.5 miles per hour. So I guess he's like jogging slowly, all right, in this example. This is how you switch between your your angular speed and your linear speed. All right, so it's 2 different ways of talking about it. Usually it helps to know the distance around whatever it is, whatever's circling. Okay. So now we want to jump to module 4, where we're going to graph. All right, we're going to graph sine, and I'm going to call it of x. Now, y'all are used to thinking about sine of theta, right? You can call this number anything you want, right? You can call it anything you want. We used to call it theta and think of it as an angle, right? You can, that helps you with the unit circle. So we have two different visualizations going on here. Here's the unit circle. That's a tool that allows us to evaluate these functions at different inputs, right? But what we want to do is we want to graph this guy, all right? Which is a different visualization of these functions. Y'all know how to graph, right? You plug a number in, see what comes out. The number in is left and right. The number out is up and down. And you plot a few points and you connect the dots, right? So there's an X and a Y over here, and there's an X and a Y over here. I mean, if you wanted to, you call this theta. Why not? Let's go ahead and call it theta for now. Then later on, we'll call it X, all right? All right, so if we're going to graph this, let's look at some points. If I plug 0 into sine, right, we use this guy. Let's see, this is 1, 0. Sine of 0 is 0. So that's the point on the graph of sine. What about like pi over 4? If I plug pi over 4 into sine, remember this is root 2 over 2, root 2 over 2. The y value there is root 2 over 2. So at pi over 4, I'd have to go up to root 2 over 2, put a point. Let's keep going. What about pi over 2? Sine of pi over 2. Well, the y value there is 1. So at pi over 2, I'd have to let me move this up a little bit. I'd have to go up to 1. So put a dot, right? We keep going, 3 pi over 4. So there's 3 pi over 4. The y value over there is still root 2 over 2, right? Sine is the y value, so we say root 2 over 2. So 3 pi over 4, we're back down to root 2 over 2. And then what about pi? Pi is over here. The y value there is 0. We're back down to 0. Okay. Now, if we keep going, let's draw a picture here. Doodle, 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 right? Now let's keep going. We keep plugging numbers in, right? Well, the bottom half of the circle is exactly the same as the top half of the circle, except all the y values are negative, and the sign is the y values. So you're going to get this same picture from 0 to 2 pi, but everything's going to be negative because all the y values down here are negative. All right. And I could keep going, right? I can keep going around the circle all I want. So this graph just keeps going and going and going. And I could have gone around the circle in the opposite direction. I could plug negative numbers into sine, so it keeps going that way. For sine, again, we're graphing sine. I should throw that. It starts right here. Sine of 0 is 0. So we know it starts at the origin, right? Right here. The angle 0 corresponds to the y value 0. Sine of 0 is 0. So this is your basic piece of sine. Everything else is just copies of that, okay? Now we know from our cofunction identities, sine of x is just cosine of pi over 2 minus x, right? The same thing goes with tangent, cotangent, secant, cosecant. That's why they're called cofunctions. All cosine is a shift of sine by pi over 2. So your cosine is going to look just like sine, except it's going to be shifted, something like that. But we like to graph it starting over here, basically. All right, and it keeps going too. So it's exactly like sine, just shifted over, okay? So cosine, though, is the even function. If you look at the graph, if you fold it over this line, it matches exactly. Sine was your odd or anti-symmetric function, and you can see that in the graph. If I took the right half of sine, flipped it over the x-axis, and then flipped it over that way, it would match. You'd have to do the double flip to make it match. That's an odd or anti-symmetric function. sometimes we talk about sine of theta. Sometimes we want to call this x and just think about it as a number, right? But don't get this x confused with the x over here. These are two different visualizations, two different x and y coordinate systems, right? There's two different ways of visualizing the same function. This was a tool that helped us evaluate sine or cosine for particular values. This is the graph of the actual function. One thing I want you to notice here is that this is not a half a circle. See, from here to here is 1, but from here to here is pi. That's 3, right? If it was a circle, right, this would have to be 2, but it's 3. So that's not like a half a circle there. It's not. It's more stretched out, okay? Let's look at some better pictures of this, though. They have a better picture in there for us. All right, so there's the basic piece of sine. All right, and again, it keeps going. So one thing you want to notice is that it repeats, right? We call the period p. For sine and cosine, it's 2 pi, all right? Because this piece, I mean, you could start here and then go to here. That length is 2 pi. You could start anywhere. 2 pi later, you're back where you started, okay? A nice visual. So I think there's a Desmos thing you'll have to do for this graphing. It has lots of animations and stuff. You're going to want to find a good graphing program. The one I use on this thing really sucks, but what I got. If you have a Mac, go to your applications utilities folder and open Grapher because it's awesome. So you can see here on the unit circle, sine is the y value. So it just so happens that the y values here are the same as the y values are here. All right. It doesn't work for cosine, right? Because over here, cosine is the x value. So don't get your x's and y's mixed up. All right, so at pi over 2, the y value is 1. So that's why here we're at 1. And here's a snapshot of your cosine. So you absolutely have to master this. If you're going to be any kind of scientist at all, you have to master this. Everything in the entire universe is sine and cosine. Cosine is just a shift of sine, so everything is a sine wave. Absolutely everything. It's called simple harmonic oscillation. In engineering and physics, you take anything that's moving, you can turn it into a system of simple harmonic oscillators. You can take any function you want. All the functions you've ever seen, you can rewrite it as a sum of sine functions, which we do all the time. Everything can be turned into a whole bunch of waves put together. Literally, the entire universe is nothing but quantum fields, which are simple harmonic oscillators, right? Everything that exists is nothing more than a bunch of sine waves added together. And here's more pictures, sine and cosine. Now these are the basics, right? Here's your sine. Here's your cosine. They look exactly the same. They both have the same period. One's just shifted over a little bit. No big deal. But what we want to do is manipulate it. Okay. So just like we started off with f of x equals x, and then we're like, oh, well, what if we multiply that x? And what if we add to it? And then we're like, hey, what about these quadratics? What about something squared? And then we're like, well, what if we multiply that or add a linear part or add something to it? What do those graphs look like? We're doing the same thing here. What are the 4 things you can do to a basic sine function? You can either multiply it or add to it, or you can mess with the input before sine even gets it. So you can multiply times the input or subtract or add from the input. Okay, those are the four things. There's four buttons here. All right, adding to sine. Right, here's your sine. Remember, sine looked like this. Doodle doodle doo doodle doo. Between -1 and 1. If you add to your old y values, that's just going to shift everything up. All right. If you multiply, that's just going to stretch your y values vertically. It's going to take sine and make it bigger. And A actually stands for amplitude. It's going to be the height of the wave. This B here, if you multiply your x, this is going to compress or stretch things horizontally. Just like outside, it stretches or compresses things vertically. That's your horizontal stretch or compression. And then subtracting, that's going to be your shift to the right or to the left, depending on what C is. So shift up, stretch up, shift left or right, stretch or compress horizontally. Okay. So think about the period. Here's this B value. The period is going to be whatever the period is of your basic function, and then you have to divide it by B. So if you think about sine, if you give it values from 0 to 2 pi, it produces a whole wave, right? Let's say I put a 2 here, though. If I put a 2 there, my x now, it only has to go from 0 to pi, but sine will receive 0 to 2 pi, and it'll make a full wave. So even though the x is going just from 0 to pi, sine is going to receive twice that. It's going to receive everything from 0 to 2 pi, so it's going to make a full wave, but the x only went to pi instead of 2 pi. So it's counterintuitive. If you put a 2 here, it's going to compress things by a factor of 2. All right. So the things that go on the inside are counterintuitive, right? Out here, if I put a 2 here, sine gets twice as big vertically. But if I put a 2 here, sine gets crushed by a factor of 2. Okay. So it's because you're acting on the x before sine gets it. And there's a reason why they have a minus here instead of a plus, right? If we add on the outside, that just moves everything up, right? Well, on the inside, it's counterintuitive. A subtraction is a shift to the right. I mean, you might think add and I go to the right. No, you subtract and you get a shift to the right. That's why they explicitly have that minus sign there. If you think about it, it kind of makes sense. It's because it's affecting the x before sine gets it, okay? And here's the trickiest part of it all right? This shift gets affected by this compression, all right? So the shift isn't going to be by C. If there is a B value there, if I have a 2 there, that compression is actually affecting the shift. The shift is only going to be half as much. The shift is what you're subtracting from the x. And here's the trick. You got a sine of bx minus c. That's the way they write it, right? Let's look at this part right here. I could factor the b out. This would be an x minus c over b. All right. The shift is what's being subtracted from the x, not what's being subtracted from bx. You see, so the shift is getting compressed or stretched as well. Okay. So that's the only tricky part. All right. So there's 4 buttons here. I'm sure plenty of y'all have played lots of video games. That PlayStation controller has like 18 buttons on it, you know. Y'all can master that and kill thousands of people in Fortnite. You can master these 4 buttons for these trig functions that you're going to use for the rest of your life. Okay. So yeah, I know it's complicated, but it's sure as hell not as complicated as any video game you've ever played. Okay. Even the old ass Nintendo 1 had at least 6 buttons on it: the up, down, left, right, GA, start, select. All right. All right. Just a matter of doing the work. That's all it is. You do the work, you'll learn. Just like going to the gym. You go to the gym and work out every day, you will build muscles, whether you want to or not. If you do a little bit of this every day, you will figure it out and it will sink in. And everything we're doing here to sine, the same stuff applies to cosine. So here you go. You got sine of 2x. Okay. So here's 4 pi. So if I double the input, I get, sorry, this one. Here's our sine of 2x. So instead of going to 2 pi, this guy produces entire wave by the time it gets to pi. And if you think about it, all these numbers, if you plug them into x, sine is receiving twice that amount. So when you plug a pi in for x, sine is receiving 2 pi. All right, so that's why it's counterintuitive when you multiply on the inside. Likewise, if I divide by 2, right, that thing is going to make things twice as big. Okay, so we talk about the period. We could also talk about the frequency. All right, the period and the frequency are just reciprocals of one another. So notice if I make the period bigger, the frequency, meaning the number of peaks, goes down, right? If I decrease the period, well, now I have more peaks, all right? So the frequency is just the reciprocal of the period, all right, if that ever pops up. And you can think, you hear the word frequency all the time, right? Electromagnetic waves, pretty much anything, right? The earth revolving, everything is frequency. Everything is vibrating at all times. So, and then here's your basic one. So you can use the unit circle to visualize these trig functions. That helps you evaluate them. And you can use the visualization of these graphs. All right, 2 separate visualizations that you want to have hardwired into your brain by the end of the semester. So we let C and D be 0. So here you go. This is going to make it bigger. This is going to compress it horizontally. Period is 2 pi over b. So let's look at sine of pi over 6 here. All right. So the period is going to be 2 pi over pi over 6, which is 12. So 12. 1 minus 1. There it is. Okay. So right here in the middle is going to be 6. So let's look at some graphs here. I'll zoom in. So notice how on the x-axis I have multiples of pi instead of 1s and 2s and 3s and 4s, right? Most graphing software has a place where you could change that. This one I had to go, it took me a while to find it. Calculate, zoom, and where is it? Edit, options. No. What edit? Axes. I had to go to axes and then x-axis. I had to click on show as multiple of pi. Okay, and that's how I turned that into pi's here. Okay, those are your basic sine function, right? If I do 2 times sine, it's just twice as tall, right? Here is sine of 2x. So it just got compressed by a factor of 2. Here is sine of x plus 2. All the y values just had 2 added to it. Okay. Here is sine of x minus pi over 4. I subtracted pi over 4. So you can see it just got shifted to the right by pi over 4. Right. Now this guy, this is 2x minus pi. So I'm subtracting pi, right? You think that would be a shift to the right by pi, but it's not. It's a shift to the right by pi over 2 because of this 2x. This 2x is making things get compressed by a factor of 2, and that includes the shift. The shift gets compressed by a factor of 2. So it's not being shifted to the right by pi. It's being shifted to the right by pi divided by 2, by that amount that we're compressing things by. All right? That's the tricky one where you have the B and the C. Does this make any sense? It's a lot, right, all at once. So what you do is whenever you're doing any of your math homework forever and ever, every time you see any function, you graph it. Use your graphing software, graph it so that you constantly have this visual reminder. A lot of the problems you do in math, it never says graph it, right? And you can usually get the answer by just evaluating it or doing something, right? But use your graphing software, do your homework, and graph that function so you can look at what you just learned and relate it to that visual. All right. They don't tell you to do that, but if you want to get this stuff down and have it just as second nature, that's the best thing to do. Okay. So here you can see they're just multiplying the output by 1, 2, 3, or 4. All right, that's all it's doing is it's increasing the amplitude. Okay, and they'll say the amplitude is half the distance from the maximum to the minimum. Well, yeah, here's the max, here's the min. Half the distance is the amplitude. All right. Yeah, put this right there. Analysis. Let's look at this guy. I like this one. This looks like sine, but upside down, right? Sine was like this, right? Well, first off, we have a 4 here. The amplitude is 4, but this thing's upside down. What that means is there's a minus. Anywhere I used to go up, instead I'm going down. And anywhere I used to go down, I'm going up. So that's all that is. A flip over the x-axis, it's just that minus sign out there. Okay. Let's see, I already said all this. Here's where they just factor out the b to show you that your shift is c divided by b. Oh, your midline. It's nice to know where the midline is, right? That helps you like figure out what's going on. Your goal is to be able to look at a graph and write down the sine function, or look at a sine function and visualize the graph, right? You want to go both ways between the visual and the analytical. All right, so this thing has been moved up by a little bit by d, right? So this is going to be sine plus d, okay? Like this one here, you got sine x plus 2. All they did was move sine up by 2. Oh, and phase shifts. We talk about phase shifts. When you shift it to the left or the right, they call that a phase shift. And you've heard the saying like, so people are in phase or something is in phase or out of phase, right? That's because of waves. Either waves can be in phase where the peaks line up, or they could be out of phase. So it's called a phase shift. All right. So here they're adding pi over 6. So what you want to think about that's a shift to the left, because it's really, you're subtracting a negative pi over 6. Okay, so that if you add, shift to the left. If you subtract, shift to the right. Remember, it's counterintuitive on the inside. All right, so let's look at this example. If I wanted to visualize this, all right, I would be like, okay, well, normally I would have sine between 1 and -1. But it's been shifted down too. So this midpoint, which was at 0, is going to be down here. I need to move this down here. So it's going to be between -1 and a -3. And let's see, there's a shift to the left by pi over 6. So this pi over 6 thing needs to go this way a little bit. Boom. Cosine, just draw your cosine, move it down 3. All right. 3 sine x, you move it up 2 and then stretch it by a factor of 3. So we can do that one. So let's see. There's our sine. So instead of being between -1 and 1, it'll be between -3 and 3. But wait, it's got moved up 2. So instead of starting at 0, it's going to start at 2. So I need to move it up 2. So it's between 2, 2 and like from here to here is 6. So that would be 2 and 3 is 5. Go up here. So it's between 2 and 5 now. Our midline here is at 2, and it has a height of 3. Amplitude is 3. So here's your basics. Your amplitude is the absolute value of A. Remember, if it's negative, that just flips it, right? But the height of the wave is still going to be the same. So it's the absolute value of the A, the amplitude. Period. Take for any function that has a period, any function that repeats, right? The period is always going to be whatever the period is of the basic function, and then divide by the number that you're multiplying the x by. Your phase shift is your C divided by B, because the shift gets compressed whenever you multiply by your x. And your D out here is your midline, where it just gets moved up or down. So if we have 3 sine 2x plus 1. Okay, well, normally we would do this, right? And it would be between -1 and 1, but that 3 says it's between -3 and 3. All right. This plus 1 says it gets moved up 1, so we'll move it up 1. 2, 1, where midline is. And this 2x says it's going to get compressed by a factor of 2. So instead of this being 2 pi here, right, it's just going to be pi. So it gets a full period in half the amount, right? The period is 2 pi divided by that number, so it's pi. Okay, 3 buttons. There you go. The picture's a lot better than mine, so it took them a lot longer to draw that. So if we look at a graph, what function is this? Let's see, it looks like a sine wave, right? But it looks upside down, right? All right, let's see. Looks like it might be shifted. How can I do this? Well, it looks more like a cosine. Remember, cosine starts up here, right? That was your cosine. It starts at 1 instead of 0. So if I look like at that, that looks like an upside down cosine. It looks like cosine got flipped over the x-axis, right? So let me try this. It looks like a flipped over cosine, so I'm going to say a negative cosine here. All right, and let's see, the period from peak to peak is 2 pi. So I know it's not stretched or pressed, and it's not shifted since I did it. If I did it as a sine, I could do it as a shifted sine, but I'm just going to do a cosine here. And let's see, it's all been moved up by a half. All right, so that's how you do it. Let's do more examples. Here's another one. This tube. Okay, so whatever it is, it's been shifted up by 2, right? It looks like a sine, right? It starts here, so let's do sine. The amplitude is 1, so I don't need anything out front. The period is 2 pi, so I don't need to multiply it by anything. It's not shifted. This is just sine x plus 2. Okay. Kind of ugly. Let's see. It looks like that's our midline. So this looks like one. This is going to be hard. Notice that these numbers are not multiples of pi. That makes me think of something like this, where you have like a multiple of pi times x. Because remember, your period is 2 pi divided by that number. So if that number has a pi in it, the pi's go away, and you end up with whole numbers here. Or maybe they were just lazy, and so it's going to be hard to tell by looking at this. But we could tell that it's been moved down by 2. Okay. And if we think about this, it looks like a sign, right? That's been shifted to the left by a little bit, right? It looks like something has been shifted to the left. So we got something here. There's a shift to the left by a little bit. What is our period? Let's see. Kind of hard to tell. From 1 to 7, the period is 6, right? Period is 6. So the period is 2 pi over whatever that b value is, right? So let's see, b is going to be 2 pi over 6 or pi over 3. I know I need a pi over 3 here, right? Now, what is this shift? Now, remember that shift is c over b, right? And we found that the b was pi over 3. So this is 3c over pi, all right? Which we have to figure out what this c is. So what is this shift? I can't tell what that value there is. It's just based on their graph. Let's see. I can't tell. If they'd have labeled that point, maybe, right? I know. I need to know how far that distance is, but it's just not really on there. But we're close. If we figured out what that distance is, whatever I'll call it, question mark, we just set this equal to question mark, solve for c, and then we know what number to put here. So this is our c. This is our new question mark, that distance. If we knew that, then we'd know what to put there. Let's see what they have in their little arsenal. So this is like the hardest you're going to get, where you have the compression and the horizontal shift. Those are the hardest ones to do. So they modeled it as a cosine instead of a sine. All right. We saw that it was shifted down by 2. We got that. We saw that the amplitude was 3. No, we didn't do that, did we? So that's the other part we forgot. From here to here is from -2 to 1. So the amplitude is 3. Forgot to do our amplitude. Period was 6. We figured that out. And then so we figured out that b had to be pi over 3. And so we got this far. Or you could have done it as a cosine. Right? Cosine is just a shifted version of sine. So these c's would be different. All right. So how did they find their c value? Cosine shifted to the right, negative cosine shifted to the right. Any of them would be correct. Somehow they know, well, they did cosine instead of sine. So if you did cosine, it would be a shift of pi over 3. But we did sine, so it's going to be a different number. Let's look at another example. Maybe this one will be labeled a little better. All right. Let's see. Here's our midline, right? So this one looks like a shift and a compression as well. All right, so let's see, it's been moved up by 4. So let's say we use sine to model this. It's been moved up by 4. Okay. The amplitude from 4 to 8, the amplitude has to be a 4. Okay. Let's look at the period. Let's see, from here to here, that looks like a distance of what, 9? Hold on. -1 to 9 is 10. So the period is a length 10, and that's your 2 pi over b. So therefore b is 2 pi over 10, or pi over 5. So we know we need a pi over 5x here. And now we just have to find our shift. And our shift is going to have a pi in it as well. Let's see if we can figure this out. So we're going, looks like our shift is a shift to the right by 1. Okay, by distance 1. So our shift was c over b, right? Our shift, which we were looking at, it's to the right is 1. Okay, it's actually negative c over b, right? So b we found was pi over 5. So this is going to be 5c over pi is equal to 1. So our shift, we could eyeball it and see that it's 1. This tells us that pi is 5c, or that c is pi over 5. So minus pi over 5. All right, that's the complicated one, right? And I think we are done for the day. I'll put this in the notes and then we'll run. Yeah. So practice. We, I forgot. Don't worry about it. Everybody gets attendance today.